So, the axial flow compressor has two main elements, which are a rotor and a stator. The rotor actually has blades that are fixed on a spindle. These blades impel air rearward in pretty much the same manner as a propeller, and that's mainly because of their angle and the airfoil contour. The rotor, turning at high speed, takes in air at the compressor inlet and impels it through a series of stages. From inlet to exit, the air flows along an axial path and is compressed at a ratio of approximately 1.25 to 1 per stage. The action of the rotor increases the compression of the air at each stage and, accelerates it rearward through several stages. With this increased velocity, energy is transferred from the compressor to the air in the form of velocity energy. The stator blades act as diffusers at each stage, partially converting high velocity to pressure. Each consecutive pair of rotor and stator blades constitutes a pressure stage. The number of rows of blades or stages is determined by the amount of air and total pressure rise required. Compressor pressure ratio increases with the number of compression stages. Most engines utilize up to 16 stages and even more. So, the stator has rows of vanes, which are, attached inside an enclosing case. The stator vanes, which are stationary, project radially toward the rotor axis and fit closely on either side of each stage of the rotor blades. In some cases, the compressor case, into which the stator vanes are fitted, is actually horizontally divided into halves. Either the upper or lower half may be removed for inspection or maintenance of rotor and stator blades. The function of the stator vanes is to receive air from the air inlet duct or from each preceding stage and increase the pressure of the air and deliver it to the next stage at the correct velocity and pressure. They also control the direction of air to each rotor stage to obtain the maximum possible compressor blade efficiency. Shown in Figure 4-3 are the rotor and stator elements of a typical axial flow compressor. The first stage rotor blades can be preceded by an inlet guide vane assembly that can be fixed or variable. The guide vanes direct the airflow into the first stage rotor blades at the proper angle and impart a swirling motion to the air entering the compressor. This pre-swirl, in the direction of engine rotation, improves the aerodynamic characteristics of the compressor by reducing drag on the first stage rotor blades. The inlet guide vanes are curved steel vanes usually welded to steel inner and outer shrouds. At the discharge end of the compressor, the stator vanes are constructed to straighten the airflow to eliminate turbulence. These vanes are called straightening vanes or the outlet vane assembly. The casings of axial flow compressors not only support the stator vanes and provide the outer wall of the axial path the air follows, but they also provide the means for extracting compressor air for various purposes. So, the stator vanes are usually made of steel, but not just any steel. They have corrosion and erosion-resistant qualities. Quite frequently, they're actually shrouded or enclosed by a band of suitable material, mainly to simplify the whole fastening problem. The vanes are welded into these shrouds, and then the outer shroud is secured to the compressor housing inner wall using radial retaining screws. Now, the rotor blades are usually made of stainless steel, but for the latter stages, they're actually made of titanium. The design for attaching the blades to the rotor disc rims can vary, but most commonly, they're fitted into discs by either bulb type or fir tree methods. After that, the blades are locked into place by different methods. Oh, and compressor blade tips are reduced in thickness by these cutouts, called blade profiles. These profiles are super important. They help prevent serious damage to the blade or housing if the blades ever contact the compressor housing. This condition can actually happen if rotor blades become, excessively loose, or if the rotor support is reduced due to a malfunctioning bearing. Even though blade profiles are designed to greatly reduce these possibilities, sometimes a blade might break under the stress of rubbing, and that can cause quite a bit of damage to compressor blades and stator vane assemblies. The blades, interestingly, vary in length from entry to discharge because the annular working space, which is the space from the drum to the casing, is reduced progressively toward the rear as the casing diameter decreases. This feature, in turn, helps provide a fairly constant velocity through the compressor, which is really important for keeping the flow of air constant. The rotor can actually feature either drum-type or disc-type construction. The drum-type rotor is made up of rings that are flanged to fit one against the other, and then the whole assembly is held together by through bolts. This kind of construction works well for low-speed compressors, where centrifugal stresses are, pretty low. So the disc-type rotor actually consists of a series of discs that are machined from aluminum forgings, and these are shrunk over a steel shaft. The rotor blades are then dovetailed into the rims of these discs. Another method of constructing the rotor is to machine both the discs and the shaft from a single aluminum forging, and then, bolt steel stub shafts onto the front and rear of the assembly. These stub shafts provide bearing support surfaces and splines for joining the turbine shaft. The combination of the compressor stages and turbine stages on a common shaft, that's what we call an engine spool. The common shaft is made by joining the turbine and compressor shafts using a suitable method. The engine spool is supported by bearings, which are seated in suitable bearing housings. So, as mentioned earlier, there are two configurations of the axial compressor currently in use. These are the single rotor or spool and the dual rotor or spool, which are also sometimes called solid spool and split spool, or two-spool, dual spool. One version of the solid spool or one-spool compressor actually uses variable inlet guide vanes. Plus, the first few rows of stator vanes are also variable. The main difference between a variable inlet guide vane, or VIGV, and a variable stator vane, or VSV, is basically their position with respect to the rotor blades. VIGVs are located in front of the rotor blades and compressors, while VSVs are positioned behind the rotor blades. The angles of the inlet guide vanes and the first several stages of the stator vanes can actually be variable. During operation, air enters the front of the engine and is directed into the compressor at the proper angle by the variable inlet guide and directed by the VSV. The air is then compressed and forced into the combustion section. A fuel nozzle that extends into each combustion liner atomizes the fuel for combustion. These variables are controlled in direct relation to the amount of power the engine is required to produce by the power lever position. So most turbofan engines are actually of the split-spool compressor type. Most large turbofan engines, use a big fan with just a few stages of compression, and that's what we call the low-pressure spool. These turbofans, they incorporate two compressors with their own turbines and interconnecting shafts, which together form two physically independent rotor systems. In fact, many dual rotor systems have rotors that turn in opposite directions, and there's no mechanical connection between them. The second spool, which is referred to as the high-pressure spool, is actually the compressor for the gas generator and the core of the engine. It supplies air to the combustion section of the engine. The advantages and disadvantages of both types of compressors are included in the following list. Even though each type has its own pros and cons, each one is used depending on the type and size of the engine.